All right, let's dive right in. We're going to talk about something pretty cool, how a tiny, simple sensor can feel a shake and turn that into a signal a computer can actually understand. It's all about going from a physical shake to a digital signal. So let's start with a basic question, right? How do you get a machine to feel anything? How does it know you've knocked on a door or if a motor is shaking too much? We basically need to give it a sense of touch, an electronic nerve ending, and that's exactly what this little guy, the vibration sensor, does. And to figure out how it works, we're going to peek inside the KY002 vibration sensor. And you'll see it's not some crazy complex piece of tech. At its heart, it's just a really, really clever switch. Yeah, this little blue module, it doesn't look like much, does it? But it's a specialist. It has one single job: feel a shock or a vibration. And just as important, its job is to do absolutely nothing when everything's calm. So, what's the secret sauce here? It's not some fancy microchip, not at all. It's actually the beautiful simplicity of just two parts. You've got a metal outer case and then this tiny, delicate spring tucked inside. That's it. This simple mechanical design is its superpower. It's why these things are so tough, so reliable, and super cheap. Okay, so picture this. When everything is still, that little spring is just hanging out, not touching anything. There's a tiny air gap between it and the casing. We call that an open circuit. But the second you shake it, that spring wiggles, it touches the inside of the case, and bam, it makes a connection. The circuit is closed. It's literally like flicking a light switch on for just a split second. I love this analogy. Think of it just like a doorbell. Normally, the button's just sitting there, but a vibration, that's your finger pressing the button. It closes the circuit for a moment, lets the electricity flow, and our project hears the ding-dong. Okay, so we've got the physical switch down. It's either on or off. But how do we turn that simple action into a language that a computer or an Arduino can actually understand? See, here's the thing. Electronics don't think in terms of on and off. They think in voltage. We call these different voltage levels high and low. And this sensor does something pretty clever. By default, when nothing's happening, its signal is high. But when that vibration hits and the switch closes, it yanks that voltage low for a moment. And that drop, that change from high to low, that's the message. That's the signal we're looking for. And this is the key takeaway, right? Your Arduino has no idea what a vibration is. It doesn't speak that language. It only understands these two states. High means everything's cool, nothing to report. But the moment it sees a low, it's like, whoa, something just happened, event detected. But wait a second. What keeps that signal from just, floating around and giving us false alarms? Well, that's where the unsung hero of this circuit comes in, the pull-up resistor. Just think of it like a spring on a screen door. It's always gently pulling that signal line high, keeping it steady. It holds it there until a real vibration comes along and gives it a good, solid tug down to low. So the sensor does the feeling, it creates the signal, but it's not the brain of the operation. It needs to report its findings to a boss, a microcontroller like an Arduino. And it's the Arduino that looks at that signal and, based on the code we write, decides what to do next. And hooking it up to that brain? Oh, it's super easy. It's just a simple 3-wire setup. You've got power, you've got ground, that just turns it on. And then that third wire, the signal pin, that's the hotline for the sensor to talk to the Arduino. Now, before our Arduino can start listening, we have to give it some instructions. We do that in the setup part of our code, which, as the name suggests, only runs once right at the beginning. We tell it, hey, listen for a message on this specific pin. And critically, we also tell it to turn on that internal pull-up resistor to make sure the line is stable. All right, once the setup is done, the main event begins. We enter the loop function, and this thing runs over and over and over again, like thousands of times a second. And its whole job is to just keep asking one single simple question. Is that pin low? Is it low now? How about now? Okay, we've looked at the mechanical bits, the electrical signal, and the code that reads it. Let's put the whole story together now. Let's follow a single shake from start to finish and see how it ends up as a message on our screen. It's such a clean, logical process when you see it all laid out. Step 1, a physical shake. Step 2, the little spring inside makes contact, closing the switch. Step 3, that connection pulls the electrical signal from high down to low. Step 4, the Arduino, which is constantly checking, sees that drop to low. And finally, step 5, it follows our instructions, in this case, just to print a message saying, hey, I felt that. And here it is in action. Look at that. Every single time we tap the sensor, a message pops up on our screen. It's proof. We've successfully taken a physical event, a little tap, and turned it into pure digital information that a computer can read and react to. How cool is that? So yeah, we've spent all this time on one tiny sensor, but why should you care? Well, because this super simple ability, just detecting a shake, is a fundamental building block for so many things you see every day. Think about it. Security systems on Windows, sensors on factory machines that can tell when something's wrong, even fitness trackers that count your steps. It all starts with this basic principle. So if you walk away with just one thing, let it be this three-part story. First, it's a simple mechanical switch. Second, it creates a digital signal by going from high to low. And third, our code is what gives that signal meaning and tells the system what to do about it. Mechanical, electrical, logical. That's the whole game. And honestly, that's the magic of all this stuff right there. Once you understand these simple core building blocks, the mechanical part, the electrical part, and the software part, you have the power to connect the real physical world to the digital world. It's the first step to taking any idea you have and actually making it real. So there you have it. You now know exactly how this works, from a tiny spring wiggling inside a can, all the way to a message on your screen. The only question left is, what are you going to build?
Hey everyone! Today we're going to crack open a tiny component that does a really big job. We're going to figure out how a simple sensor can actually feel a physical vibration and turn it into data a computer can use. Let's dive right in.
So let's start with a pretty cool question. How do we teach a machine to feel? How do we get it to react to a knock on a door, a tilt, or even a tiny tremor? Well, in the world of electronics, we need something like a nerve ending to translate those real-world events into a language our projects can actually understand.
And the solution, as you've probably guessed, is a special little component. This is the first step on our journey, getting to know the tool we're going to use to give our machine that sense of touch.
Now, you might think this sounds super complicated, but here's the thing that might just blow your mind. At its very heart, this sensor is really just a simple, clever little switch.
I mean, the beauty of this thing is just how simple it is. Forget about complex microchips for a second. The entire mechanism comes down to just two parts. You've got a conductive metal can on the outside and a delicate little spring tucked away on the inside. Seriously, that's it.
So, how do these two simple parts work? Well, check it out. On the left, you see it when it's just sitting still. The spring isn't touching the casing. See that gap? That means electricity can't flow through. We call that an open circuit. It's basically like a light switch in the off position. But the moment a vibration hits it, bam! That spring wiggles around and makes contact with the outer casing. That closes the circuit. And for just a split second, the switch is on.
A great way to think about this is like a doorbell. When nobody's there, the button isn't pressed and nothing happens. A vibration is just like a finger coming along and pressing that button. It completes the circuit for a moment, and that lets the signal ring through.
Okay, so this is the really crucial part, how that mechanical on and off becomes a digital message. See, our electronics don't really see on or off, they see voltage levels. We call them high and low. And this sensor has a really clever setup. Its normal default state is being held at a high voltage. The vibration, that moment the circuit closes, it yanks that voltage down to low. That drop from high to low, that is the signal. That's the entire message.
But wait a second, how does it stay high in the first place? This is where our unsung hero comes in, the pull-up resistor. Without it, the signal would just be floating, kind of like a door swinging in the breeze. You'd never know if it was truly open or closed. This resistor, it acts like a strong spring on that door, firmly holding it shut, keeping the signal in that stable, high state. A vibration is the only thing strong enough to provide a real push and pull that signal low. It gives us a super clear, absolutely unmistakable signal every time.
Okay, so we have a signal. Now what? The sensor did its job, it felt the shake, but it can't think for itself. To actually make sense of this signal, we need to connect it to a brain.
You see, the KY002 is just a messenger. It needs to report what it found to a microcontroller, something like this popular Arduino board. The Arduino is the real brain of the operation. It gets that low signal and then decides what to do about it, based on the code we upload.
And you're gonna love this part. Hooking it up is so simple. It's just a 3-wire setup. 1 wire for power, 1 for ground to complete the circuit, and then that all-important 3rd wire for the signal. That's the path our little low message takes to get from the sensor straight to the Arduino's brain. So we've got the feeling, we've got the brain, and we have the connection. The last piece of this puzzle is the intelligence, the code that tells the brain exactly what it should be listening for.
Arduino code is awesome because it's pretty much broken down into two main jobs. First, you've got the setup function. That runs just one time, right when you power it on, to get everything ready. And then you have the loop function, which, you guessed it, does exactly that. It runs over and over and over again, forever, constantly keeping an eye on the sensor.
So let's just peek inside that setup function. First, we tell the Arduino which pin to listen on. And then, with just one line of code, we activate that internal pull-up resistor we were just talking about. This is us basically saying, hey, Arduino, keep that line at high voltage and don't let it budge unless you hear a real signal. And finally, we just open up a communication line so it can talk back to our computer.
All right, now for the action. The loop function is basically asking one simple question over and over, thousands of times a second. Is the signal low? If the answer's no, it just asks again. But if the answer is yes, it triggers an action. In this case, it sends the message signal detected right to our computer.
So let's put all these pieces together. We're going to trace the entire journey from a physical shake all the way to a real result that we can actually see on our screen.
And here it is, the whole story in one picture. A physical shake closes the mechanical switch. That pulls the electrical signal from its normal high state down to low. The Arduino code, which is always checking, finally gets the yes it was waiting for, and it triggers the output. It's a perfect little chain reaction. And this is the payoff. This is what you see on your computer screen. Every single time that sensor gets a tap or a shake, signal detected pops up. We've done it. We have successfully translated a physical event from the real world into digital information that our machine can understand and act on.
So why does this matter? Well, because this super simple ability is the fundamental building block for tons of amazing applications. Think about a security system that detects a window breaking, or a machine in a factory that can feel when it's vibrating in a bad way. Even the fitness tracker on your wrist that counts your steps. It all comes down to this exact same principle.
So here's your takeaway. Number 1, at its heart, it's just a mechanical switch. Number 2, it sends a digital signal by pulling a high voltage low. And number 3, we use code to give it the logic, to check for that signal and decide what to do. Mechanical, electrical, and logical. That's the whole shebang.
And really, that's all there is to it. The mystery is gone. You now understand the principle from start to finish, so the only thing left to do is to take this knowledge and go build something awesome with it.
Which brings us to a final question. We've given you the tools, you've got the understanding. So now that you can teach a machine to feel a little piece of the world around it, what's the very first thing you're going to teach it?